Hello friends, very good morning to all of you. Here myself Amul Gandule. I am going to teach you the inorganic chemistry of your MSc first year. The course name is CCTP2 and the old course code was CHI 130. It is inorganic chemistry of semester first. Okay, and in this inorganic chemistry paper we are going to discuss here the second section, that is chemistry of main group elements. So dear friends, we know that what are main group elements. So the main group elements are the S block and P block of the periodic table. Togetherly they are known as main group elements. Okay, so basically this inorganic chemistry and second section of this inorganic chemistry paper is comprising of the study of periodic table, mainly S and P block. Okay, so S block has two groups, that is group number 1 and group number 2. Group number 1 is known as alkali metals and group number 2 is known as alkaline earth metals. Then group number 3 to group number 12, from 3 to 12 it consists of D block, that is transition elements. Okay, it is consisting of D block elements, and after 12 the group number 13 is the first group of P block element. So 13 to 18, group number 13 to 18, they are consisting of group P block elements. Okay, and S and P block togetherly they are known as main group elements. Today we are going to start here the fourth chapter, that is carbon group elements. So carbon group elements are mainly 5 elements are there. So carbon, silicon, germanium, tin and lead. Okay, so C, Si, Ge, Sn and Pb, these are the symbols of these elements: carbon, silicon, germanium, tin and lead. Okay, so out of these 5 elements, so first element is totally non-metal, that is carbon is totally metallic in nature. Okay, the last 2 members of this family, of this group, that is tin and lead, are metallic in nature, while the silicon and germanium are known as metalloids. Okay, so a variation from the non-metallic to metallic character has been observed in group number 14. Okay, so here we are sticking to our syllabus. Our first point in this chapter is allotropes of carbon. Okay, so first of all, before going to start the details of allotropes of carbon, let us see the definition of allotrope and allotropy. So what are these allotropes? Allotropes are nothing but different physical forms of the same element. Okay, when the same element is existing in the nature in the different forms, all that forms of that element are called as allotropes of that element. Okay, and the phenomenon or this concept is known as allotropy. This phenomenon of existing of the same element in different forms, okay, is called as allotropes, and this phenomenon or concept is known as allotropy. So carbon is existing in the different allotropes. Okay, mainly there are 4 allotropes of carbon can be seen in the nature, in the atmosphere, and these are diamond, graphite, graphene and fullerene. Okay, so there are mainly 4 allotropes of carbon have been seen, and these are diamond, graphite, graphene and fullerene. Okay, so we are going to study in detail about these 4 allotropes of carbon. So let us see first. So the first one is diamond. Everyone is familiar with this word diamond, but very few of us know that this diamond is consisting of only and only carbon atoms. Okay, someone might be get confused how it is. Yes, the answer is yes, because this diamond is consisting of only one element, that is carbon. No other element is present in that carbon, and hence this is one of the form of carbon which exists in the nature. Okay, so carbon is existing in the nature in the form of diamond, and we know that diamond is one of the precious gems, one of the precious gems. Okay, so it has high demand in the gems, jewelry, and etc. Okay, in that ornamental field, this diamond has a lot of value. Okay, so it has lustrous, it is very lustrous in nature, it is shining, highly pure and attractive in nature. So come to the chemistry of diamond. Diamond is one of the purest form. Diamond is one of the purest form of the carbon source in the earth itself. Okay, in diamond, each carbon atom is sp3 hybridized. In diamond, we are going to study here the structure of diamond. So in diamond, each carbon atom is sp3 hybridized. Means what? Each carbon atom is tetrahedrally attached to other 4 carbon atoms. Here one should keep in mind that we have habit that whenever it is sp3 hybridization of carbon atom, methane is coming in our mind. Methane is coming in your mind, and that methane is having carbon with 4 hydrogen atoms. So notice that diamond is not having hydrogen atom at all. Okay, not a single hydrogen atom is attached to that carbon in diamond structure. All 4 valency of that sp3 tetrahedral carbon atom are balanced by, or they are joined by other 4 carbon atoms. This is the main difference that you should keep in mind. Okay, so each carbon atom is sp3 hybridized, and each carbon atom is tetrahedrally bonded to other 4 carbon atoms. Okay, so that's why all the 4 bonds, that is tetrahedral, the central carbon atom, let us say, just like is in methane. Okay, for this is taken only for your simplicity. Okay, so this is central carbon atom, let us say, and this central carbon atom, let us say, is bonded to other 4 carbon atoms, carbon, 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 not any other element. Okay, not any other atom. Okay, and all are single sigma covalent bonds. All bonds in this carbon diamond structure are single sigma covalent bonds. Okay, the bond length is 1.54 angstrom units. The bond length is 1.54 angstrom units. Okay, so the bond length is fixed. Carbon carbon single bond length in diamond structure is 1.54 angstrom units. Okay, so as 2-dimensional structure is shown here in front of you on the board, I have written. Okay, but this is only 2-dimensional. The picturization of 3-dimensional structure of this diamond is not possible on this board or on paper. Okay, so look at this. Each carbon atom here, this is carbon atom. Okay, or sorry, this carbon atom. Okay, so 1, 2, 3 and 4. Okay, so this is the skeleton of this diamond structure. Okay, so each carbon atom is 1, 2, 3 and 4. Each carbon atom is tetrahedrally bonded to other 4 carbon atoms. Okay, so this is the skeleton of diamond structure present in the structure itself. Okay, then this tetrahedra, all these tetrahedra, 1, 2, 3, 4. So all these tetrahedra linked together, all these tetrahedra linked together in a 3-dimensional network. In a 3-dimensional network, to form a giant molecule. To form a giant molecule means giant means very big molecule. Okay, so very big molecule is formed by the linking of all these tetrahedron togetherly. Okay, and the melting point of this diamond is extremely high. It is almost about 4000 degrees Celsius. Okay, but the round figure is 3930 degrees Celsius. Okay, it is very hard in nature. We know that diamond is known to be one of the hardest material on the earth crust or on the earth surface. It is one of the hardest material. Okay, so it is very hard. Why it is so? What is the reason? Because all bonds are single sigma covalent bonds, and all these bonds are strong covalent bonds. All these bonds are strong covalent bonds, and these bonds are forming a tetrahedron, and all these tetrahedron are extended in the three-dimensional manner. Okay, so in all possible x, y, z three-dimensional manner of an coordinate axis, and it is forming a giant molecule. Okay, so that's why it is very hard. It is very hard to break these covalent bonds. Okay, strong covalent bonds. It is not an easy task. It is a very hard task to break these covalent bonds, and hence this is the reason why the diamond is very hardest material on the or in the nature itself. Okay, then it is having high density and high refractive index. So it is having high density, high values of density and refractive index. So it is as refractive index is very high, so it is very attractive and very clear. Okay, so that's why the peoples are also attracting towards the diamond for getting that diamond. Okay, in gems and jewelry. Then it is a good conductor of heat. Diamond is a good conductor of heat, but it is a bad conductor of electricity. Okay, so diamond is not passing, or it is not transforming electricity. Okay, but it is transfer heat. Okay, so heat is transferred, it is conducted, but electricity is not conducted. So this is all about the structure of diamond. Okay, so you have to remember the key points regarding this diamond. Okay, all carbon atoms are sp3 hybridized. Each carbon atom is tetrahedrally joined to all to other 4 carbon atoms in a tetrahedral manner. Okay, and that tetrahedron is expanding in 3-dimensional view, in 3-dimensional manner, in all possible directions. Okay, in 3 dimensions, and it is forming a giant big molecule, and all the covalent bonds are very strong. So that's why it is one of the hardest material. Okay, the bond length is 1.54 angstrom units. So this is all about the diamond. Now next one is the graphite. So graphite is the second allotrope of carbon element. It is again one of the purest form of carbon. The nature of graphite is, it is lustrous in nature. Okay, but it is having grayish or blackish color. Okay, the structure of this graphite, it is consisting of flat 2-dimensional sheets of carbon atom. Flat 2-dimensional sheets. Okay, so diamond is 3-dimensional, but graphite is 2-dimensional. Graphite is consisting of flat hexagonal rings of carbon atom. Okay, and they are in 2 dimensionals. Okay, each sheet is a hexagonal net of carbon atom. Each sheet means all these sheets are arranged either in 2 ways. Okay, that we are going to see in the coming article of this graphite. Okay, so each sheet is hexagonal array, hexagonal net or array of carbon atoms. Okay, just like benzene, but it is not just like benzene. Benzene is aromatic in nature, graphite is not aromatic. Okay, so the structure of graphite sheets is shown here. Okay, so you may call this is exactly looking like a benzene ring structure, but this is not a benzene ring. Okay, so it is aromatic sextate is not complete here. Okay, so that's why it is not like a benzene. So this, let us see here, this is the first layer, this is the first layer, let us say this is the second layer, okay, and this is the third layer. In this figure this is third layer, but this third layer is repeating exactly above the first layer, exactly above the first layer. Okay, so this is the structure of alpha graphite. This alpha graphite means what? Graphite is existing in two forms, that is alpha graphite and beta graphite. All these two forms are interconvertible to each other, okay, and these two sheets are repeating in AB manner, AB manner. Okay, so first layer, second layer, this is first layer, let us say like this, this is second layer, and third layer is again repeating like this. This is first layer, this is second layer, and third layer again repeating on the first. Okay, it is exactly similar to that of first layer. So this is what AB sheets or AB repeating manner of graphite. Okay, you may have studied this in solid test chemistry, that is structure of solids. Okay, the beta form is having three sheets, that is ABC. Repetition is after three sheets. Okay, so 1 2 3 and A is coming after 3. So this is the fashion, or this is the trend of repetition of hexagonal rings in the beta form of graphite. Okay, these alpha and beta graphite forms are interconvertible. Okay, on heating beta is converted to alpha, on heating beta form of graphite is converted to alpha, and on grinding means churning, okay, this alpha is converted to beta. Okay, these sheets, that is hexagonal array or hexagonal net of carbon atoms, okay, they are held together by weak forces that are known as van der Waals forces. Okay, the layers, the first layer, second layer, third layer. Okay, so these layers are held together by weak van der Waals forces of attraction. Okay, so the situation is like this, the situation is like this. This is the structure of graphite. Okay, so this is first layer, this is second layer, and this is third layer. All these sheets or rings, hexagonal rings, are held together, they are held together by these dotted lines, and these dotted lines are known as weak van der Waals forces of attraction. Okay, so these sheets are arranged in graphite. Okay, so there is a repetition of these sheets, and these sheets are made up of only and only carbon atoms, only and only carbon atoms. Okay, there is no any hydrogen atom. Okay, and there is a stacking, let us say we call it as stacking of layers of carbon, sheets of carbon atoms are there in graphite structure, and they are repeated either in AB manner or in ABC manner. Okay, so this is a very simple structure of graphite. Now coming to the structure and bonding of this graphite, in this graphite molecule, in this graphite structure, the carbon-carbon bond length is 1.41 angstrom units, 1.41 angstrom units, which is very similar to that of the bond length which is observed in benzene. Okay, so bond length in benzene is 1.40 angstrom units, so it is very similar to that of benzene. Okay, why it is so, that we are learning here. Okay, the distance between two layers, so this is the distance between two layers, so this is first layer, this is second layer. This layer is also made up of hexagonal rings of carbon atom, this layer is also made up of hexagonal rings of carbon atoms. Second layer, first layer, second, all are carbon atoms, and the distance between these two layers is 3.35 angstrom units. Each carbon atom in graphite is sp2 hybridized. Each carbon atom in graphite is sp2 hybridized, means only 3 valence electrons of that carbon atom are utilized here to form sigma bonds, to form sigma covalent bonds, and the 4th valence electron is used here for the formation of pi bond, fourth valence electron is used for the formation of a pi bond, and this is the case. This is pi bond. On each carbon atom there is a fourth electron, and which is forming a pi bond with the adjacent carbon atoms. Okay, and these pi electrons are responsible for the delocalization. These pi electrons are not localized. Okay, they are delocalized electrons, means they are not localized at one place, they are continuously delocalizing, and this is the reason why graphite is a good conductor of electricity. Okay, we know that the graphite has many uses, and in old days, not now, in old ions, means the thing which we are using for the ironing of our clothes. Okay, and in that the graphite material is used for heating that plate or coil. Okay, and hence this is the reason why graphite is a good conductor of electricity. So these mobile electrons or these pi electrons are responsible for the conduction of electricity in the graphite itself. Okay, we know that this graphite is also a good conductor of heat as well as a good conductor of electricity. Then this graphite is also used as a lubricant. The graphite is also used as a lubricant. Okay, so this is all about the structure of graphite and the explanation about the graphite. Okay, now the third allotrope of carbon is graphene. Okay, third allotrope is graphene. Now we are going to see the third allotrope, that is graphene. So in graphene, again, as this graphene is also, this word is derived from the graphite itself, but the structural pattern of graphene is different than that of graphite. Okay, so what is the difference? Graphene is consisting of a single sheet of or a monolayer or a single sheet of hexagonal rings of carbon atoms. Hexagonal rings of carbon atoms. Okay, so this is the main thing about, we can say, the graphene. Okay, so it is consisting of single layer of carbon atoms arranged in a two-dimensional honeycomb like structure. Arranged in a two-dimensional honeycomb like structure. Honeycomb like structure or lattice. Okay, so this is the honeycomb like structure, means instead of here I can show you on this. Okay, so this is the structure of graphene. Okay, so hexagonal rings are arranged in a two-dimensional way. Okay, and this is exactly looking like a honeycomb like lattice. Honeycomb means beehive. Okay, so it is a honeycomb like beehive structure is looking like that. Okay, so this is the structure of graphite. Okay, so this pattern is repeating in all. Okay, so this is the sheet, and this is a monolayer or a single layer of carbon atoms. Okay, forming a hexagonal rings, and all these rings are made up of carbon atoms. Okay, then like graphite, each layer of graphene is made up of hexagonal rings that I have shown, and they are giving a honeycomb like appearance. They are giving. Okay, then properties of graphene: it is highly pure in nature. Then graphene is the strongest material. Graphene is also one of the strongest material. Graphite is soft. Note down here, graphite is soft, but graphene is hard. Graphene is hardest material. How much it is harder? When we compare this graphene to that of steel, then this graphene is 200 times more harder than stainless steel. We know the stainless steel, all these construction and buildings are made up of stainless steel material. Okay, so it is 200 times greater harder than the stainless steel. Okay, so this is the major difference between graphene and graphite. Mind well, graphite is totally soft in nature, while graphene is hardest material. Then it is both stiff and elastic. It is both stiff and elastic. So we can stretch, as it is elastic in nature, we can stretch this graphene material to form or to elongate without breaking. Okay, then it is very light in weight, though it is harder, but it is very light in weight. This is contrasting properties. Okay, and it has very high thermal conductivity. It has very high thermal conductivity, as well as it is a good conductor of electricity by the transfer of electrons, transport of electrons. Okay, so this is all about the graphene. Okay, good conductor of heat and electricity. It is a good conductor of heat and electricity, and it is very light in weight. Okay, it is hardest material. Okay, so these are the main properties of graphene. Okay, now the fourth allotrope of carbon is fullerene. Fourth allotrope of carbon, it is recently researched by the scientist Fullerene. Okay, so fullerene, what are fullerenes? Fullerenes are the cluster type of forms of carbon atoms, cluster forms of carbon atoms or carbon elements. How it is formed, or how they are, when they are occurring? When two graphite electrodes, electric spark is struck between two graphite electrodes. So this is the situation when an electric spark is struck between the two graphite electrodes. A blackish or a soot is formed, soot is produced, and this soot that is carbon black, this soot or carbon black is formed when electric spark is struck between the two graphite electrodes. Okay, and this soot is consisting significant amount of, okay, means important, significant means large amount of, it is, this soot is consisting of large amount of this fullerene material. Okay, this C60 molecules or carbon cluster compounds. Okay, this is consisting of C60 cluster compounds, C60 cluster compounds, and this C60 means carbon 60. Such type of compounds are observed in this soot, and these cluster compounds are having a cluster of 60 carbon atoms together. Okay, and they are known as fullerenes or Buckminster fullerene. Buckminster fullerene. Okay, or the nature of this Buckminster fullerene is just like a saucer ball, hence it is also called as buckyball. It looks like a saucer ball. Okay, saucer balls means it is just like a football. Saucer means football. Okay, and hence it is looking like a, it is known as buckyball. Okay, the structure is like this. All these carbon 60 cluster, they are arranged on this buckyball structure. It is a three-dimensional. mind well, this is a 3-dimensional cluster. C60 is a 3-dimensional cluster, okay, and it is composed of 60 carbon atoms arranged over the surface of that saucer ball, okay, just imagine like that, and they are made up of 5-membered and 6-membered carbon rings. 5-membered and 6-membered carbon rings, okay. So this is the situation. So this is a 5-membered ring, 1 2 3 4 5. This is 6-membered ring, 1 2 3 4 5 6, okay, and this is the okay. It is just for your information. This surface of this buckyball or Buckminster Fullerene is composed of 5-membered and 6-membered rings. As there are 60 carbon atoms, there are 12 5-membered rings. It is consisting of 12 5-membered rings, okay. So 12 into 5-membered rings, 12 5s are 60, and 26 membered rings, okay, 26 membered rings, okay. So this buckyball is consisting of 26 membered rings and 12 5-membered rings, okay. These fullerenes are covalent in nature. These fullerenes are covalent in nature, okay. So all bonds are covalent, and it is covalent in nature, and hence it is soluble in organic solvents. It is soluble in organic solvents, okay. Then these C60 carbon clusters or Buckminster Fullerene molecules can be oxidized or reduced. They can be oxidized or reduced, okay. When they undergo reduction, they form a clathrate compound with alkali metals, and they are forming K3C60, okay. So this K3C60 type of compounds, they are found by the electrochemical reduction with the first group elements, okay. So potassium is the first group element, and this K3C60, such molecules can be act as a superconductors. They can be act as a superconductors. They are acting as a superconductors at 18 Kelvin temperature. At 18 Kelvin temperature means this is a very low temperature. We know that 273 degrees Celsius is equal to 0 Kelvin. This is a relation, okay. So 18 kelvins means 273 plus 18. 273 plus 18 means round about 7 8 90 291, sorry, minus 273 degrees Celsius is equal to 0 Kelvin, okay. This is the relation. So you can convert this 18 Kelvin into degrees Celsius. So this is very low temperature in degrees Celsius, okay. So at this temperature, this K3C60 is acting as a superconductor. So these are some applications of this fullerene, okay. Like these C60 molecules or C60 clusters or molecules, another type of clusters can be found just like this, okay. And this is the main difference between the graphite, diamond and fullerene, okay. So graphite and diamond, they are forming they are existing in a 2-dimensional graphite and 3-dimensional diamond, okay, array. But these fullerenes they are forming cluster compounds of carbon atoms, okay. So this is the difference between the allotropes of carbon atoms, okay. So in this way, here we have seen all these 4 allotropes of carbon consisting of diamond, graphite, graphene and fullerene, okay. Thanks for watching this video. Have a nice day.